Hello everyone, I'm Haoqing, and today I will talk about the deep learning of GNSS signal correlation, co-authored by Parisa, Borhani-Darian, Peng, and Closas. And this is the outline of my presentation today. At first, I will introduce some basics of GNSS, the classical signal processing, multipath problem, and its influence in GNSS. And then I will talk about the deep neural network applied in the paper, the goal of this model, its application, the corresponding structures, and hyperparameters. And finally, the simulation results are provided, as well as the conclusions and future work. So first, the GNSS classical signal processing. As the equation 1 shows, in the general model, we assume the GNSS signal received is consisted of the modulated navigation message, as well as the white Gaussian noise. And therefore, according to the least square method, to achieve the optimal estimation of time delay and Doppler shift, we need to maximize the cross-ambiguity function, which is the correlation between GNSS signal and its local replica. However, that's just the ideal assumption. In real world, GNSS signal can easily be influenced by different kinds of interferences, such as the jamming signals or the multipath. And as the figure on the left shows, multipath is a time-delayed version of GNSS signal, and therefore it can easily cause distortion in the correlation results, which is shown in the figure on the right. And because of these distorted correlation results, the estimation of time delay can also be biased, especially in the tracking block. And therefore, to solve this problem, we need to find a way to remove the multipath effect from correlation results, which is shown as the diagram below. And to simulate the correlation triangle accurately, 61 correlators are applied over -2 chips to 2 chips, while 41 of them focus on -0.2 chips to 0.2 chips. And to achieve this goal, the deep neural network in this paper is applied to substitute the classical correlation in the tracking block, which is shown in the diagram below. And as this diagram shows, the input for this deep neural network is the real and imaginary part of GNSS complex signal, as well as the PRN code. And the output of this deep neural network is IQ samples from correlation. And by this way, we can decrease the influence of multipaths. This slide shows the structure of our model. So as the diagram below shows, the deep neural network in this paper is consisted of 2 main blocks, the regression block and the classification block. But at the very beginning, we have a convolutional layer to simulate the classical correlation method. And considering the existence of multipaths, we can call these correlation results as non-outside correlation results, Y2. And with this Y2 as our input for the regression block, we can estimate the non-outside correlation result YY, with multipath influence removed. However, this regression block can only work well with the existence of multipaths, and therefore we need a classification block to help us to further decide whether the multipaths exist or not. And as the diagram shows, with Y1 and Y2 both as input for this classification block, the output is a binary label to decide whether we are in non-alpha case or non-alpha case, with the corresponding probability W1 and W2. And to get the final output of the whole deep neural network, we need to do a weighted average at last, with the corresponding probabilities W1 and W2, as well as the correlation results Y1 and Y2. And by this way, we can remove the influence of multipaths. We know that the two blocks in the diagram is trained independently. And this slide shows some hyperparameters of this deep neural network. The number of layers in each block, the active functions, initial learning rate, training apples, the size of training dataset and test dataset, optimizer, and batch size. I know that the threshold of the relative delay between GNSS signal and the multipath to decide whether we are in the non-alpha case or non-alpha case varies with different early late spacing. For example, with early late spacing as 1 trips, this threshold would be 1.5 trips relative delay. And therefore, different classification models are trained, and the early spacing chosen in this paper are 1 trip, 0.2 trips, and 0.1 trips. And here is some simulation settings. In this paper, the model is trained only by GPS-L1 signal, with PRN equals 1 to 0.2. And the clear towards noise density ratio, the CL1 dot, varies from 37 to 43 dBHz. The Doppler shift varies from -1000 Hz to 1000 Hz, and the relative delays between GNSS signal and multipath change from 0 trips to 6 trips. And to test the performance of this model, the early minus rate discriminator is used in the simulation. And now the simulation results. This slide shows the noiseless multipath envelope with single multipath injected, and the corresponding signal-to-multipath ratio is 5.2 dB. And as this figure shows, when multipath exists, the neural network would always outperform the classical method with all 3 different early-late spacing. And even when the multipath goes beyond correlated spacing, which means we are in the non-alpha case, the 2 methods still hold a similar performance, which is shown in the subplot in the figure. I know that the vibrations in this subplot is caused by the pseudo-noise, the cross-correlation between GNSS signal and its local replica. And the same thing happens if we have signal-to-multipath ratio at 3 dB. However, if we further increase the multipath power to get signal-to-multipath ratio at 0.97 dB, things would be a bit different. So if we check this figure carefully, we can find that around 0 trips, the classical method would be a bit better compared with the neural network, especially with early spacing at 0.1 trips. However, in other cases, the neural network still holds its advantage. And that's in the non-alpha case. And in the non-alpha case, the 2 methods still hold a similar performance, which is shown in the subplot. And that's all for the noiseless simulation. If we inject noise into our dataset to get signal to noise density ratio as 43 dBHz, we can see the degraded performance of neural network. However, even at this case, the neural network still outperforms classical method when multipaths exist. And when we are in the non-alpha case with no multipaths, the 2 methods still share a similar performance, which is shown in the subplot. And the same thing happens if we have a signal-to-multipath ratio at 3 dB. However, if we further increase its multipath power to get signal-to-multipath ratio at 0.97 dB, we can see a clear decrease, degraded performance for the neural network, especially with destructive multipath interference. However, even at this case, the neural network still performs similarly as the classical one. And that's for the non-alpha case. When multipath goes beyond the correlated spacing, which means we are in the non-alpha case, the two methods still hold a similar performance. And to show this trend for different CR windows, we have the mean square error of the time delay estimation in the non-alpha case versus different CR windows. And as the figure in this slide shows, in general, the neural network would always perform the classical method. However, if we check this figure carefully, in the lower CR1 dot case, for example, when the CR1 dot equals to 35 dBHz, the classical method would be a bit better in terms of lower mean square error. And this can be explained by the fact that the model is only trained with dataset whose CR1 dot varies between 37 dBHz to 43 dBHz. And if we keep increasing our data size to include more CR1 dots, this problem should be solved. And here we have the signal to multipath ratio as 5.2 dB. And if we increase the multipath power to get signal to multipath ratio at 3 dB, we would have a similar result. However, with larger multipaths, things would be a bit different. In this slide, we have signal to multipath ratio at 0.97 dB. And we can find that although the neural network still outperforms classical methods with only spacing as 1 chip or as 0.2 chips, the neural network would lose its advantage with the early spacing at 0.1 chips. And that would be our future work to improve. And finally, the loss of efficiency in the general case when there's no multipath. And here we can find that even without the existence of multipaths, the neural network can still hold its advantage compared with the classical method. And we can also notice that in the lower CR1 dot, the neural network would lose its advantage, but it can still be solved by increasing the size of our training dataset. And that's all for my simulation results. Finally, the conclusions and future work. This neural network-based correlation method improves robustness against multipaths in most cases. And the loss of efficiency in the non-alpha case is also degraded compared with the classical method. However, the narrow correlator needs to be further improved against the large amplitude multipaths. And the multiple multipath cases should be simulated in the future to test the performance of neural network-based correlation method. And that's all for my presentation. Thank you.